Chapter 6 is all about set theory. Before we can do operations on sets or even write proofs about sets, we need to understand how sets work. So we're going to start with a few definitions that come from section 1.2. So you can read an introduction to what set theory is in the notes, and I will say that it is one of the most important mathematical concepts because set theory is involved in pretty much every aspect of higher math. So let's start with recalling that a set is a collection of mathematical objects with a common characteristic. Sets are comprised of elements that are contained in curly braces, and we use the element sign to signify that an element is in a set. Likewise, if we put a line through it, that means that our element is not in the set. So we've been using these symbols for quite a while now. But what we haven't talked about yet are subsets. So if A and B are sets, then A is called a subset, and it is written as A, and then the sideways, it almost looks like a sideways U with a line underneath it, and then B. And that is if and only if every element of A is also an element of set B. So our official definition here says A is a subset of B if and only if for every x, if x is an element in A, then x is an element in B. So that is the only way for A to be a subset of B is that every element that is contained in set A is also contained in set B. More specifically, A is a proper subset of B if and only if every element of A is in set B, but there's at least one more element in B that is not in A. We're not going to be concerning ourselves too much with the difference between a subset and a proper subset. It's just one of those definitions I really wanted you to have access to. So a proper subset is a subset that has fewer elements than its original. We call the set of all possible objects with some broad characteristic a universal set, which we would call U. If there is at least one element of A, then is not an element of B, then A is not a subset of B. So A, officially A is not a subset of B if and only if there exists an element X such that X is an element of A and X is not an element of B. A short note on our universal sets. A universal set could be things like the set of all integers, the set of all rational numbers, a set of real numbers. Those could all be universal sets, but so could the numbers 1 to 10. So could the alphabet. There's a list of, there's an unlimited number of ways we could define a universal set. It's really dependent on the problem that we are looking at. So if we looked at, say, example 6.1.1, we have A as the set 1, 2, 3, 4, 5. And part D says, to which universal set do you think A belongs? Well, that could be that just A is our universal set, 1, 2, 3, 4, 5. It could be that U is the set of positive integers. Maybe it's Z plus. Maybe it's all integers. Maybe it's all real numbers. Maybe it's the positive rationals. The list is endless, right? So our list here is endless. So let's start back at A. What are some of the elements of A? Well, A's elements are 1, 2, 3, 4, and 5. Those are the collected members of set A. We call them elements. Some of the subsets of A. Let's see, we would have maybe just 1, maybe just 2. How about 3, 4, and 5 together? Let's see here, maybe 1 and 5, maybe 2 and 4. Ooh, we could do 1, 3, 5. That would be the odd integers in the set. There's a whole bunch of them. So, which of our subsets that we listed here would be proper subsets of A? Well, honestly, all of them, unless we listed a subset of 1, 2, 3, 4, and 5. So if we add our 1, 2, 3, 4, and 5, we then can say that all of the other subsets are proper. So 1, 2, 3, 4, 5 are proper subsets. 1, 2, 3, 4, 5 is not because it's the same size. Let's see here, 1, 5, 2, 4, and 1, 3, 5. Those would all be our proper subsets. And this is really the only time we're going to talk about proper subsets. So I just wanted to give you that idea of the difference between a subset and a proper subset. Can the empty set, the null set, be a subset of A? And the answer is yes. The null set, which we call this 0 with a slash through it, is a subset. So is a subset of every set. So how do we prove or disprove subset relations? Well, because we define what it means for one set to be a subset of another by means of a universal conditional statement, we can use the method of direct proof to establish a subset relationship. We call this an element argument form of proof. And when you see in the homework to do an element argument proof, this is what we're talking about. So it's the fundamental proof technique for set theory. So how does an element argument proof work? We're going to let sets A and B be given. To prove that A is a subset of B, we're going to suppose that X is a particular but arbitrarily chosen element of A, and then we are going to show then that X is also an element of B. Sounds easy enough. Let's see how it works in action. In example 6.1.2, we have the sets A and B, and they are defined as set A is the set of integers m such that m is equal to 6r plus 12 for some r in the set of integers. Set B is an integer n such that n is equal to 3s for some s in the set of integers. So let's see how we would go about proving that A is a subset of B. Well, the funny thing is here, our statement is literally going to be that A is a subset of B. And our element argument proof says first, then we're going to suppose X is an element in A. By the definition of A, right, A is given by that truth set there. So by the definition of that truth set A, X then, if it's an element in that set, is equal to 6r plus 12 for some integer r. So for some r in the set of integers. So that means then X is also, if we factor out a 3, 2r plus 4. If we let S equal 2r plus 4, then we know that S is an integer because integers are closed under addition and multiplication. right? So thus, we have that x is equal to 3s for some integer s. Well, by the definition of set B, right, by the definition of set B, that means that x is also in set B, right? So it follows that for all x in set A, x is in set B. And therefore, by the definition of subset, that we saw on the first page, A is a subset of B. So this is a fairly simple and straightforward example, and this is for a very specific definition of set A and a very specific definition of set B. When we want to get into more abstract values for sets A and B, where we don't define them to be limited to any specific operation here, like m is 6r plus 12, that's what we're going to get into in sections 6.2 and 6.3. And we're going to learn how to write proofs and disproofs. In fact, we can do a disproof for this one. We're going to disprove that B is a subset of A. So here we only need, remember, we only need one counterexample because we have a universal statement. So we only need one counterexample. So the example I'm going to say is let x equal 3. Then x is an element in B because 3 equals 3 times 1, and 1 is an integer. However, 3 is not an element in set A because if it were, 3 would equal 6r plus 12, which means negative 9 would equal 6r, and negative 3 halves would equal r, which implies then that r is not an element in the set of integers. So therefore, 3 is not an element in A. And thus, B is not a subset of A. One of the most important properties of sets that we're going to be looking at is going to be this idea of set equality. So given sets A and B, A is equal to B if and only if every element of A is in B and every element of B is in A. So our formal definition says A equals B if and only if A is a subset of B and B is a subset of A. So when we write element argument proofs trying to prove equality, we are going to have to write cases. We're going to have to show that A is a subset of B, and we're going to have to show that B is a subset of A. So we are going to do that right away with example 6.1.3, and this is something we're going to do a lot in sections 6.2 and 6.3. So let's define sets A and B as follows. A is the set of integers m such that m equals 2a for some integer a. And B is the set of integers n such that n equals 2b minus 2 for some integer b. We want to know, is A equal to B? Well, let's try it. Let's see. Our statement would be that A equals B for the given sets A and B. So you notice we don't have these universal conditionals that we had in chapter 4. They're a little different now. So proof here, our proof is going to say we're going to suppose that A and B are the given sets. A and B are the given sets. Now what we're going to find out is when we get into sections 6.2 and 6.3, we're going to be letting A and B be any sets, and we're going to be proving properties that are true or disproving properties that are false from any kind of set. So set relations that apply to all sets. So that is going to be a really interesting skill to have. So we're going to start with our case one where we're going to show that A is a subset of B. It doesn't matter which one you start with. I always start with the one on the left though, and then I go to the one on the right. So our element argument proof says we suppose X is an element in A. Then we're going to be tasked with showing that X is an element in B. So by the definition of A, by the definition of set A, X equals 2A for some integer A. And if we let B equal a certain value, and how are we going to find that value? Well, let's think about it. We'll write ourselves some notes over here. We are trying to show, that X equals 2 times an integer minus 2. So if we say then that X is 2A, then 2A is 2 times an integer minus 2. And if we solve for that integer that we're specifically looking for that would make this work, we would say then 2A plus 2 would equal 2 times the integer. And if we divide it all by 2, we would just have that A plus 1 would be that integer. We're going to call that integer B. So B is now equal to A plus 1. Let's see what that means in terms of our sets then. Because then we know B is an integer because integers are closed under addition. So we know that B is still an integer. Then, by the definition of B, 2B minus 2 is in the set of integers. So by substitution, we can see then that 2B minus 2 is going to be equal to 2 times A plus 1 minus 2, or 2A plus 2 minus 2, which is 2A. And what did we say was equal to 2A? That's right, we said that was X. So from back here, we pulled in the X equals 2A here. From our A plus 1 here, we pulled it in there. So now we have just shown that X is also in B. So thus, X is also in set B. And therefore, by the definition of subset, A is a subset of B. Now the question is, does it go back the other direction? Well, let's see. see, we would have B is a subset of A. Well, we're going to let X be an element in set B now. By the definition of set B, then X is equal to 2B minus 2 for some B in the set of integers. And just like before, we were trying to show, let's see here, we are trying to show again now, we're trying to show, right, that X is equal to 2 times an integer. So remember, that's where we started on the first case. This time, that's where we're going to. So we want to show that it's 2 times some integer. And the nice thing is this one actually comes across a lot quicker. So we're going to say, let A equal a specific value. That value is going to be, well, let's go find out. Well, what we're looking for is that element in set B, that X, that 2B minus 2, we want it to equal 2 times some integer. Which means that if we divide it all by 2, we get B minus 1 is that integer. So we're going to let A equal B minus 1. Well, that seems interesting. Let's see what happens then. Then we know that A is an integer because integers are closed under subtraction. So we have that one. And then, by the definition of A now, remember we're going back the other direction, by the definition of A, let's see here, we have 2A is an element of A. So by substitution, we know that 2A is now equal to 2 times our B minus 1. Right? Remember our B minus 1 from earlier? Well, what that means then is that this is 2B minus 2. And what is 2B minus 2? That is our X from this time. So we said that back here. So here's our 2B minus 2, and here's our X. So we started with an X that was in B, and now our X is in A. We'd say thus, X is in set A. And therefore, by the definition of subset, B is a subset of A. And it follows, by the definition of set equality, that set A equals set B. And we are finished. The true heart of set theory is when we start talking about operations on sets. So we let A and B be the subsets of the universal set U, then we can define the union of A and B to be the set of all elements that are in A or B, including elements that are in both A and B. So our official definition here says that A union B is the set of elements X in the universal set such that X is in A or X is in B. And note to those of you who are used to programming, this is not an exclusive OR. So in an exclusive OR, the only elements would be the ones that are strictly only in A or only in B. Versus this is a mathematical OR where we will also allow elements that are in both A and B. The intersection of A and B is the set of all elements that are common to both A and B. So A intersection B is the set of elements X in our universal set such that X is in A and X is in B. The key here is the difference is that a union is an OR and an intersection is an AND. So you can think of these in terms of our logic from chapter 2 as a disjunction and a conjunction. So you probably remember this as being similar to like P or Q, and this one as P and Q. So similar concepts. Then we have something a little different, no pun intended, and that is the difference of B minus A is the set of all elements that are in B and not in A. So you remove from set B any element that is in set A. So it says that B minus A is the set of X, which are elements in the universal set, such that X is an element in B and X is not an element in A. There is not a logical equivalent for that one in terms of chapter 2. But for the complement, we actually do have a logical version of this one. So the complement of A is the set of all elements in the universal set that are not in A. So A's complement is a set of elements X that are in the universal set such that X is not in A. So this is akin to our not P. So how do we look at these operations on sets and determine how they work? Well, the nice thing is we can draw Venn diagrams. And you've probably heard of Venn diagrams before, and we're going to be drawing them in this class. We're going to be using them again in section 6.3 to help us build disproofs. So they're a wonderful tool for visualizing unions, intersections, differences, and complements. So we're going to draw the Venns for each of the above operations. So while it's difficult for me to draw this in my video making app, I drew this in my note-taking app, and it will be part of the solutions that are posted. So when we draw Venn diagrams, we draw one large rectangle to represent the entire universal set. So everything is contained within this rectangle. Then we have a circle for each set. So here we only have sets A and B. So we have a circle for set A, a circle for set B, and we have an area where they overlap. So the union would be where we would highlight and color in anything that was in set A or anything that was in set B. So visually, it's anything within either circle. And are the elements that are in set A and also in B, so it's only where they overlap here in this little football-shaped piece in the middle. If I said A minus B, it means I take all of the elements in A, but remove from set A any elements it shares with B. Likewise, if I did B minus A and found the difference of set B with set A, I would take all of the elements in set B, but remove this little football shape in the middle of any elements that it shares with A. And the last one is the complement of A. Well, it's everything that is not in A. So you notice A is the only thing not colored in. Everything else is colored in. So A's complement is everything in the universal set that is not in A. So now that we've looked at Venns and we can sort of visualize what's going on here, we can try to do some of these operations on specific sets with very specific elements. If we let U be our universal set and it is the letters A, B, C, D, E, F, G, and then we're going to let A be the subset A, C, E, G, B is the subset D, E, F, G, Then we want to find A union B, A intersection B, B minus A, and A complement. Once we find those, then we're also going to find A minus B, B's complement, the complement of A intersection B, the complement of A union B, A complement intersected with B complement, and A complement union with B complement. Sounds like a lot. Let's just start at the beginning. A union B is going to be the set of elements that are in either set A or set B. Well, A has A, C, E, and G, and B has D, E, F, and G. So we would have together A, C, D, E, F, and G. But if I wanted to find out what A intersection B is, that's the set of elements that they have in common. Well, it's not A, it's not C. Oh, but E and G, they both have E, and they both have element G. If I look at B minus A, I'm going to take the elements of B, D, E, F, G, and subtract from it any elements that it shares with A. Well, it shares E and G, so all that's left are D and F. And A's complement is any element that's in the universal set that is not in A. So that would be B. Let's see, we have C, we don't have D. We have E, we don't have F, but we do have G. So it looks like just B, D, and F. If we want to try some more of our operations here, let's see here. So if we found A minus B, it's all of the elements in A minus any elements it shares with B, which are just E and G. So if we take A and remove E and G, we're only left with A and C. If we look at the complement of B, it's going to be all of the elements that are in the universal set that are not in B. So A, B, and C, well, we have D, E, F, and G. Oh, well, that's it then, just A, B, and C. If we look at the complement of A intersection B, we know that the intersection of A and B is the set E and G. And we want to find its complement, meaning all of the elements that are in the universal set that are not E and G. So we would have A, B, C, D, and F. Interesting how that happens. If we look at A union B's complement, then we're looking at the complement of, well, A union B was A, C, D, E, F, and G. And its complement is any element that is in the universal set that is not in this union. And the only one that's missing is the element B. If we wanted to see what A complement intersected with B complement is, we can look at our A complement was B, D, and F, and we can intersect that with our B complement, which was A, B, and C. And the only element they have in common is B. Our last one is A complement union with B complement. So we can see from the previous example, that's BDF union with ABC. So we have AB, CDF. For example 6.1.5, there are Venn diagrams that are associated with each of these examples that you can check out in the posted solutions. We're going to look at the more analytic version of the solutions here, but I highly suggest checking out the Venn diagrams. They're just a bit hard for me to draw in here. So if I wanted to look at this example, I have the universal set is still A, B, C, D, E, F, G, but now it's broken down into 3 different subsets. Subset A is A, C, E, G, subset B is D, E, F, G, and subset C is a set B, E. So if I wanted to look at A, union B, union C, I'm looking at A, C, E, and G unioned with D, E, F, and G, which is also then unioned with B and E. So if we look through all of those elements, we find out that we get all of these letters, A, B, C, D, E, F, and G. So our solution would be A, B, C, D, E, F, and G, which is also our universal set. And I put serifs on the top, those little lines, so that we know it's not a union. It means the universal set. Let's try looking at the same sets, but now instead of unions, let's try intersections. So let's intersect A, C, E, and G with D, E, F, and G. Well, we did that one before, and we found out that their intersection of A and B was only E and G. So let's see if C has any of those elements. Let's see here. So C has B and E. So the only element that is common to all three subsets is the element E. If we wanted to look at a few other operations here, we've got A union C's complement. Well, let's look at what A union C is first. A is the set A, C, E, and G, and we want to union it with set C, which is just elements B and E. And then we want to take its complement. Well, let's union them first. So we get A, B, C, E, and G. Well, the complement would be any element that's in the universal set that is not included in this set yet, which would be, let's see, we have A, B, C. We do not have D, E, we don't have F. So it would just be D and F. Well, let's do the same thing with the intersection. The intersection of A, C, E, and G with B and E is only going to be, we already found this out earlier, the element E. And we want to find its complement, any element that's in the universal set that is not E. So that would be A, B, C, D, F, and G. And the last two operations we're going to do on this problem are going to be the set differences of C and A and C. We're going to compare the two to see that they don't look exactly the same. If we did A minus C, we have the set A, C, E, G, and we want to remove from it elements B and E. The only element that A has that can be removed by removing C is just element E. So you notice there's not going to be this deficit of that B. B wasn't in, it was not an element in set A to begin with, so there's no need to remove it because it was never there. So we're left with just A, C, and G because we removed the part of element C, the part of set C that was in set A. But let's see when we do C and we remove from it set A. Well, then we have B and E, and we want to remove A, C, E, and G. Well, this time the only thing they have in common is still the E, but C only started with B and E, so the only thing, right, the only element it has left is just B. So it's clear that the difference A minus C is not the same as C minus A.